Good afternoon, everyone. My name is Desmond Martin. I'm the Chief Learning Officer at NextWaveSTEM, and it is my very good pleasure to have you with us. I'm really excited. This is our first webinar in a little bit of a while. We've taken a little bit of a break as the summer's come to a close, and we know that schools are starting back up, making big shifts and changes than what we've seen in the past 18 months. These new changes, these new shifts in what we've been doing in the last almost 2 years have meant that we've had the opportunity to really reconsider ways in which we approach STEM, get creative in the ways that we engage our students with hands-on learning opportunities, but also have taught us to be flexible, have taught us to prepare for a future that we can't necessarily imagine. And a great way to do that is through the tool of project-based learning. So in today's webinar, we're going to have the opportunity to really dig into how we can use project-based learning with a particular focus on STEM-centered emerging technologies. We're going to be looking at one use case, one particular technology usage with respect to drones, something that we've launched here at NextWaveSTEM that we're really excited about. But these techniques, these tools, these considerations are going to be applicable to whatever you're doing in your school, in your district, whatever your goals are with respect to STEM and getting higher engagement and better STEM outcomes for your students. Project-based learning is a great way to go about that. So really excited to spend just a little bit of time talking about that today. Before we do jump into that, however, I do want to take a bit of a moment just to go over just our logistical ground rules here for the webinar. The first is that we are indeed in webinar mode. So that means that even though I'm sure that you are camera ready, you're dressed to the nines, and you've got a beautiful speaking voice ready to share your insight and wisdom, we unfortunately won't be able to see your face today, and we won't be able to hear your voice today. However, that does not mean that you are voiceless. The chat functionality is open. That means that if you have any questions, any comments, any interesting commentary that you might add to our discussion today, you are more than happy to do so. I'll be monitoring the chat, and that means that you can drop something in, and we'll be sure to pick up right on top of that as soon as we get started. Additionally to the chat being open, the Q&A functionality is also open. If you have any questions that you want to keep anonymous, that you don't want to share with the entire group via the chat, you are more than free to do so. We'll make sure to get those questions answered for you either live during the course of our webinar, or we set aside just a few minutes at the very end to get your questions answered as well. The last bit of housekeeping before we get started is that if you need to step away from the webinar, that is okay. We do plan to go until about 5 o'clock, but because you're joining us live on our webinar today, your registration means that you will also get a copy of this recording. Feel free to share this information with your colleagues, with your teachers, with your decision makers, with your STEM department, science, math, technology heads. If you like what you see, feel free to pass this along so that we're getting a good word out there about what we are doing at NextWaveSTEM. With all that being said, we can go right ahead and jump in to our discussion today. A great place to begin is really at the beginning. And at NextWaveSTEM, we believe that everything that we do stems from our philosophy and our goal. And now, without focusing too much on what's happening on the slide deck, detailing what that philosophy is, we can really encapsulate that with the belief that students belong in STEM fields. We want them to be hands-on. Yes, we want them to build their confidence, and we want them to be able to experience and do these things without failure of messing up, without failure of getting it wrong. But the reason why we want to do that is because we believe that all students have a place, have the potential to belong in STEM. And the reason why we think that's true, and the reason why we believe it's critical that it's true, is that we're empowering teachers of today with our curricular materials, with the training, with the equipment to prepare students for the future. And the thing about the future is that we cannot predict what will happen. If you asked any one of us whether we would spend the better part of almost 2 years completely relearning how we deliver lessons, learning how we deliver content, making adjustments for our physical learning spaces, in a lot of ways, fundamentally relearning the pedagogy that we might have learned as educators so that we can continue to educate our students, there was no way that any of us could have predicted that. And in the same way that we couldn't have predicted the situation that the pandemic has placed so many of us in, we don't know what the future will hold. But we do believe, and we've seen it proven true, that technological solutions, scientists, engineers, and mathematicians are going to be key, going to be critical to coming to those solutions. So for our students to be ready for that future that they can't predict, we want to make sure they have the tools to be able to respond. And that really starts with the fact that these solutions are going to come from our students' hands-on learning experiences and opportunities with emerging technologies in STEM. So at NextWaveSTEM, that's who we are, that's what we believe. What we do, something that's really important to us is this ability to inject emerging technologies into the classroom. And when we talk about emerging technologies, we're talking about things like robotics and artificial intelligence, drone technology, 3D printing, and also the opportunities for our students to learn more about solar power, cybersecurity, the Internet of Things. We're giving our students at a young age hands-on experiences with technologies so that as they matriculate, they hit the high school level, they hit the career and technical education track, they go into the tertiary level of education. There's already a level of comfort that will inspire and set a really great foundation for positive STEM outcomes. Higher test scores, more professionals working in industries, more capacity, more desperately needed capacity to solve problems, both big and little. Our courses, the curricula that we offer at NextWaveSTEM, are really designed to help meet your needs with respect to alignment. All of our courses are NGSS grade band aligned, but they're also aligned to Common Core Math and ELA standards while bolstering 21st century skills. In NextWaveSTEM material, you'll find not only these cool, engaging hands-on experiences, but you're also going to get this opportunity to meet your particular assessment. So with that being said, we can really jump into this webinar and consider what it will look like for us to get started with project-based learning, what kind of materials that we might consider, and we can even think about techniques, especially in this pandemic and post-pandemic paradigm that we now share. We need to make sure that we are consistently flexible as we teach and as we select our materials. So a great place to begin then is defining this idea of project-based learning. We are hearing this acronym PBL, project-based learning, and sometimes that's also subbed in with problem-based learning. They're very similar ideas, but at their heart, the idea of project-based learning is that students would gain the knowledge and skills to be able to progress in their coursework by working over a really extended amount of time with that particular subject matter. Now, that might sound like really basic pedagogical understanding, but it's different than some of the rote work that we might have seen in traditional mathematics or science education. The idea isn't to just dump a bunch of facts onto our students and have them be able to reiterate those facts or develop skills and then new skills and move on. Instead, what we want our students to do is consider a real world application for a science or technology or engineering or mathematics or an amalgamation of those different disciplines. Think about what thing we can change, what problem we can fix. And then as we're studying, we're building the skills consistently to a place where we might be able to present solutions to those problems. This longitudinal style thinking means that we would consider project-based learning not in the perspective of units that might be done in the course of a few weeks or even a month, but we should be thinking about whole semesters or whole quarters or entire school years as we work through project-based learning. And the history of this is really, really long. Even to ancient Hellenistic times, you have scholars and educators like Confucius and Aristotle who believe that's important to question, but also do hands-on learning. When we get into the 20th century and reformist styles of education, we know that the giants of education pedagogy, like John Dewey and Maria Montessori and Jean Piaget, really believe that our physical environment, the ability to get hands-on, but also getting hands-on and working through a physical environment that's driven by our students' own self-interest, things that will actually connect to their experiences, lead to much deeper learning, and honestly lead to much more robust and much more reliable outcomes. So when we're thinking about hands-on learning and we're thinking about project-based learning, the really important relationship that we want to build between the two, we contrast that to what we might consider in rote learning, traditional education pedagogy. We might consider really projects, what we might see at the end of that rote learning path as a dessert. We are taking this opportunity to launch a unit. We get started on the first day, and then we do a lesson, we do an activity, and we follow that cycle. Lesson, activity, there may be some assessments in the form of quizzes. Our homework, student-generated work is useful for that as well. But we're going on this path. Lesson, activity. We finish this, do an assessment at the end, our unit quiz, and then there's a project, kind of as ice cream on the top. Sometimes that becomes really important in what we assess for our students. Oftentimes it's really useful as a hands-on fun thing to do, something to break up the monotony of the work that the students have been doing so far. But we're really used to seeing this model. And the data tells us that this is not great for one, keeping students interested, or two, helping drive students into these STEM outcomes, especially in the context of science and technology education. Instead, it's important for us to consider what we might consider a whole meal approach, not just the ice cream at the end, but this really nourishing educational experience. So when we think about project-based learning in the overarching instructional model, we begin with a driving question. This is the portion that our students should be extremely invested in. Something that we're invested in as educators, but something that gives our students a why to continue to come back and be excited to learn about what we're learning about, especially in emerging technologies. From there, we continue to dive into this idea of inquiry and research. Our students are going to have to pull in information they absolutely don't know, because for this question to be interesting, for it to be engaging, our students really can't already know the answer. I've never asked a question that I thought was interesting that I also believed I already knew the answer to. Not in good faith, at least. I'll say it that way. It's important for us to give our students questions and let them choose questions that they actually want to learn more about. From there, and a really big part of this, and mostly just laid out in the way that we might frame a project-based learning experience, is student choice. This is absolutely critical. We're there as guidance, we're there steering our students, but we never want to take away our students' abilities to decide which next point of student work is going to help get them to their solutions. It's going to help get them to their final problems that they're solving. That's critical. And what we'll see is this opportunity for our student work to be extremely diversified. So this gives us a really, really interesting and dynamic way with which we give our students more differentiated instruction, more differentiated attention for our students. And all this means that we're going to have some really unique, really engaging student learning experiences. The students will design this project, actually work through the solution that they want to present, and we're working as a feedback loop. Not only us as instructors, but their peers and the whole community. And I say the whole community because once again, we're really interested in exploring solutions that are applicable for the real world. Finally, our students will absolutely need to present the solution. What we do in project-based learning does not live in the black box of our classrooms. For those who have these real world problems, whether it's our students or their families or the school community or the actual physical communities surrounding our schools, our neighborhoods, our zip codes, our cities, there should be a dialogue and a feedback about the kind of solutions that are being proposed for these problems. Because, especially because we're working in the field that integrates engineering. And when we do engineering, we're solving human problems. We're doing these things with human beings in mind. That means we need their feedback. And not only is it good practice, it's not only good pedagogy with respect to teaching, but it's also a just way of thinking about the ways in which we apply technological solutions. Doing that critical step is really going to build life skills for our students in ways in which we can avoid some of the most crucial potential future problems that we might run into. And finally, there's this reflection moment where our students will think about their entire learning experience and consider how important this question was to them, how important it is to their communities at large, and what the new driving questions will be. Our students are making real meaningful experiences from this project-based learning. It's going to drive not only what they learn and the kind of skills they acquire, but also the directions and the choices that they'll make to apply their education towards the betterment of human society, if they still choose to do so. The project-based learning instructional model is longitudinal and brings in a lot of different considerations, but they are critical to really developing the next generation of well-equipped STEM learners. So what we'll have the opportunity to consider at this point is defining what might be a project-based learning unit. I know we've already used that analogy of the traditional project being a dessert, and then we might have the project-based learning being this whole meal, but what does that mean practically? Well, we actually have a more robust kind of tree of decisions that allow our students to really drive the work that's going on. But as this is happening, we're also given this really unique opportunity as educators to synthesize what our students are doing and point them in really useful directions. What we should consider is the project launch. And that's what we're going to do today when we think about where to get started. When we launch a project, we're really digging into this idea of exploring a question that matters, something that our students will explore and consider throughout the course of the project. We're narrowing our project and our driving question a little bit because we're focused on technological solutions. But the cool thing about technology, especially emerging technology, is it has this amazing way of capturing our imagination. Looking at our slide deck, we'll see this interesting kind of slide design where we have things that are highlighted in green, our segments that are highlighted in blue, as well as segments that are highlighted in red. When we consider our segments highlighted in green, we're thinking of really joint work between our students and our teachers and our instructors. But the blue sections are chevrons that get really, really diverse. Right after our project launch becomes student-driven work. This is work where our preparation and our delivery of learning rubrics for our students helps give our students the guidance that they need to go out and own this work on their own. And this can look like a plethora of different things. We might have particular activities that help us learn concepts or build skills. We might bring in experts or Zoom in experts that will be able to present us new information and give us insight that we as instructors just don't have a technical background on. We might actually conduct labs and experimentation, proving scientific concepts or testing really specific ideas within our driving questions. We may make models. We may conduct interviews. We may run complete technical simulations. We may actually build and use the technology to apply to a task We may completely write up a different kind of scenario for our final presentation. All these different ways in which we can attack student work and many others means that the learning path for our students, whether they're working individually or working in groups, is really, really, really unique. However, on the back side of that student work event, however much time is dedicated, whether it's a day or whether it might be an entire week, we have this idea of benchmarking because we want to assess. We want to, using those rubrics that we've laid out for all the different types of student work we might integrate, then benchmark that work. How original is this? How much skill acquisition did they get? How good a job can they do in articulating what they've learned and what they've acquired and what they can do across several media? That's a really important 21st century skill for our students. Just like we have our rubrics for our students to be able to present their student-driven work, we have our own assessment rubrics that allow us to really drill into what our students are learning. And then that reflection moment becomes a guidance point. Perhaps our students have been going through project-based learning and all of their work has been really focused on research. They're doing a really good job of synthesizing information in a vacuum, but they have not yet prepared anything to share that solution with anything else. Their next point of student work might get narrowed down by us as instructors, where they'll need to present to their classmates, or they might need to present or prepare a presentation that might be uploaded to YouTube to be shared, or they might even work beyond the context of just their classroom and individual work and get out into the community to have community interaction. We're set as a guidepost. What we see is this continual feedback loop of student work, benchmarking, and then reflection pointing to new student work. Eventually, we get to our final events, where that deliverable is going to be presented as a final solution. And that's going to be our school community, our classrooms, our community at large. And then that final reflection, where students are really making the most meaning out of what's happening. Lots of different places to go, lots of places for us to point, but everything roots in and is driven by the idea with what happens in the project launch, which is our driving question. So we want to consider the right place to start. This is critical for what we do at NextWaveSTEM when we consider project-based learning. Should be critical for any project-based learning that you'll do with your students, especially as we're pulling in emerging technologies. So how exactly do we, in concert with our students, actually choose an appropriate driving question? Something that's going to hook us as educators and make us really excited to teach the technology, something that's going to draw our students to return to the classroom day after day, excited to learn. Context is key. I can't emphasize that enough with respect to the driving question. Context is key. And what we should do is not think in abstraction when we consider a driving question. We should think about something that's going on in the real world, something that's being discussed, something that's being considered in our communities, whether that's hyperlocal to our just school community or to our neighborhood community, in our state, national, or international communities. What we are thinking about is what problem currently exists. If we're thinking specifically about drones, and we'll talk about that some more, we have to think about the context in which drones are being used, and the problems we hear about people having using drones. Are they using them safely? Are they using them legal? We consider what tools we have available for us to solve the problems. If we're exploring and learning more about emerging technologies, we'll know that we'll have our drones available to us. The equipment kit that we provide in NextWaveSTEM complements your entire class with drones to be able to fly drones in a few different modalities. So we'll actually have the real equipment. We're not going to be thinking abstractly once again. We're going to fly the drone. And then this idea that ensuring that those who are solving the problem, our students, are those who are receiving the solution are actually receiving a real solution. If there's a problem with the way drones are being operated in our local context, how do I make sure that the people who have a problem are actually getting a solution? So that might look like skill acquisition that's purely technological, but we can easily imagine that this might look like skill acquisition and skill building that's also legislative, that's also social studies. We're building a lot of different skill sets that are going to help us get to where we go when we think about project-based learning. The amazing thing is our students might take us places that we had not previously considered. So let's think about drones for a moment. When we think about drone technology, and this is going to be our case study, this emerging technology specifically of drones, we're considering a technology that has traditionally, really from its inception in the way that we know it today, been a military tool. We know that for many of us as adults, our conceptualization of drones is going to be very different than younger students' conceptualizations just because of the generations in which we live. And we can see it even in the data, in the Google search data. The usage of the word drone throughout the 20th century was pretty flat. There's a little bit of a spike in around 1950 or so, but then it drops down to flat for decades and decades. And then we see a hockey stick curve right around 2001 because of the usage of drones for military applications. We understand that as adults, but for many of our students, their first experience with drones will be completely recreationally. They'll see the drone that they can purchase from their local store, purchase online, and that means that there's this kind of disconnect. So right away, we're given this amazing opportunity to explore a little bit further with our students what drones are actually capable of. Whether we're seeing drones being used for public safety and security applications, literally around the world. That includes both military and non-military use, domestic uses. But a really, really exciting sector for drone technologies is going to be in the delivery space, where we're seeing the future face of logistics potentially changing overnight because of the ways in which drones might be used. Just these two contexts alone, and what our students think about this, what they wonder about this, the excitement of actually flying the drone in a hands-on, engaging way, means that there are lots of different questions and lots of different problems for us to consider that we want to answer through our driving question. What's also really important to consider is that we want to make sure that we have the tools that allow us to answer these questions. That means that not only are we flying drones manually, which is really fun, which is really engaging, but if we are completely transparent, not that different than operating a remote-controlled aircraft or remote-controlled helicopter, right? For us, it's important that we understand drone usage in a more robust way, what we see in the real world when we think about security and delivery applications. So that means that we need to be able to fly our drones autonomously as well, using computer code to give our drones instructions. That means that we don't have to manually fly that drone. Right? Your students will press a button after they've given the drone a set of instructions, and the drones will fly themselves. We want to make sure that our students, when they're thinking about drones and they're thinking about questions of delivery, don't have to go out there and manually fly the drone every time they explore some idea in drone delivery, because that's not the real world. In the real world, with the technology that we want to make sure our students have access to, we want them to be able to combine computer science learning as well. So when we create this context, we have problems where we have to consider things like security or even privacy, or we are thinking about logistics and delivery, or we're considering the physics. What will this mean to build bigger, more capable machines to solve these problems, or the legality and the ethics? Should we even be using these technologies in these ways? What will it take to legislate around these problems? We have to consider what it means for our student-led work to be driven forward. Where should our student-led work go from here? Well, the first thing that we want to understand is actually physically what our drones do and how they'll work, what they're able to do for us, how we're able to expand, and even some flexibility in the way that we use our drones. We can use drones inside and outside the context of our courses, especially when we're considering project-based learning. So when we're flying drones, we're integrating a few disciplines that are key to our students' next levels of learning. There's computer science, of course. They're going to be learning computer languages, Scratch, drag and drop coding, which is really, really great for our students who have minimal exposure to computer science or have lots of exposure to Scratch, where they're learning more logic and less syntax. But the great thing is that our drones are always expandable. They expand and can be programmed using Python coding as well. For our students, especially at the high school level, who are taking those computer science principles classes and are growing into higher level orders of languages, Python is the most taught computer science language in the United States of America at the K through 12 level. This becomes critical. But we're also building in scientific understanding of physics, because we basically have a flying robot. We have to stabilize a mechanical system that's using power, that's displacing volumes of air. There's so much that our students have to understand about the drone just even hovering. And then finally, once again, we're solving human problems. So we're integrating engineering. Now, while that's great to think about what that means for us from a cross-disciplinary perspective, in the real world, what we're able to do is simulate these flights. We're able to actually program our drone even via the internet and see what this drone flying in the real world would do before we ever actually fly the drone. But then in connecting to our drone for both the manual and autonomous flights, we can actually fly abstractions of these real world applications. We might not deliver the actual Amazon package, but we can do that in facsimile using our drone. And then we're connecting other tools for both science and scientific exploration, because our drones usually have sensors like thermometers or infrared rangefinders, or our camera, which is a really, really useful sensor. We're able to record more about what's happening in the world around us. Both simulators and manual flight, using code, understanding the scientific process, solving real world problems from a human perspective means that the student work can jump in a lot of different perspectives. But we know for a fact that whatever is going to happen, there's a really, really great chance, almost essential opportunity for our students to learn how to fly drones in multiple ways. So that goes back to, once again, this whole idea of that focus, really focus on the student-led work. That might be learning code. That might be practicing simulations. That might be flying outdoors. That might be running obstacle course and tests so that they become better manual flight or better manual drone pilots. That can be practicing their videography skills. That could be establishing ethical rules of code and conduct. All these things should be wrapped in and are wrapped into what we consider when we do project-based learning using drone technology. And the actual assessment work, the ways in which we guide our students can follow in with what we want to explore in our driving question. So let's actually see this in action a little bit. Let's simulate flying our drone. Let's get a sense of what this actually looks like with an autonomous flight simulation. NextWaveSTEM, we are really, really fortunate to partner with an amazing drone technology company called DroneBlocks. DroneBlocks allows us to do Scratch-based programming. It allows us to simulate our flight just as long as we're working on a browser. But we're also able to connect to our physical drones using DroneBlocks for manual, not manual flight, but for autonomous flight, where we could just press a button and our real-world drone flies by itself. It's available for PCs via your browser. Chrome works best, but it will work in other browsers as well. And also available for iOS and Android. And that means that regardless of what kind of technology situation you have, you'll be able to fly your drones. Let's take a quick look at what that looks like. And for that, I'm just going to jump into another tab. This is our DroneBlock simulator. And we can see here our drone sitting on the right-hand side of our screen, kind of in this stark, empty three-dimensional space. If I zoom in and change the view of our drone slightly, we'll actually see this nice DJI drone that we use in our course. This is the real drone that we use. They put it directly into the simulator. The only difference is that the back of this drone is blue, as opposed to what you would find right out of the box, which is white, just for visual contrast, making sure that we can see everything in our simulated space, and especially keep up with our drone. When we consider students who are having their first opportunities to learn about computer science, to learn how to code, to fly a drone, it makes a lot of sense for us, especially if we as administrators and we as educators have only flown the drone maybe a few times or never before. This might be our first experience. It makes sense for us to explore really how this machine is going to move. And by combining this with drag and drop coding, we're able to actually simulate flights. I can tell the drone to lift off into the air, and instead of having to do really robust Python coding where I have to be concerned if I miss the comma someplace or miss the semicolon or I don't have a bracket closed and my code doesn't work, I'm just snapping my instructions together. It's actually so easy that I might be able to speak in natural English what I expect the drone to do. Flying our drones, we're able to adjust our units of measurement between inches and centimeters. I'm a huge fan of flying in centimeters, especially because our drones work really well indoors and outdoors. Our drones, this case, a Tello drone that I have here, we'll do a live fly test in our webinar with our drone as well, is the kind of drone that works really well in multiple situations. In the classroom, in the hallway, in your auditorium, out on your playground, on your football field, you've got the opportunity now to really not be hampered by your physical environment. So we'll give the drone some simple instructions. We'll tell the drone to fly forward. We'll tell it to increase in altitude a little bit. Say we might want it to have a better view of what it's seeing. And then we want, of course, something a little celebratory as well. Our drones do have the ability to do flips, for example. That's something that's really fun for our students, is to have their drones fly or being controlled by the computer software, and then execute this really, really cool motion at the very end. Finally, after doing all this work, we'll tell our drone to land. In the span of 45 seconds and with 5 blocks of computer code where I haven't typed anything other than to change the numbers, change the distances that the drone is going to fly, we've constructed an entire program, something that's going to allow us to see the drone in the context of flying. Opening up the menu and launching the mission, we see our drone in the air. And this is what we would see in the real world as our drone flies as well. I'm going to attempt to be a little bit of a better cameraman. Our drones really show us computer control and machine control. And while it's really cool to see this in a simulation, the idea that connecting the same computer code to our physical drone, and that we can do it just that easily, where our drone is flown, changed position, done a really cool flip, and then ended up landing, means that our students are going to be able to jump in right away, building their skills in computer science while considering things like outside factors that might affect the drone, the difference between the simulation versus the real world ways in which systems work, which is a directly accessible next generation science standard, as well as considering what good flight looks like when we are flying drones in the real world. Our heads are really being wrapped around the technology from the get-go. When we're flying our drones, we're not just controlling the motion of the drone and doing simple things like going forward. Of course, we can manipulate our drones in all 3 physical dimensions, forward and backward, left and right, and up and down, but we're able to access more robust computing logic, extending and building in loops so that there's going to be automatic flight patterns that our drones can fly. We can create algebraic and even calculus thinking and pre-calculus thinking for our students. When we consider mathematically the ability to build and change variables in the middle of flight, And we can even go further, building and writing entire subroutines. Scratch is powerful in that we not only have to work with just a few blocks and a few lines of code like what I just showed, but we can have dozens or even hundreds of blocks of code. And we can really consider ways in which we are packaging our code up in really easy to use ways in the context of a program. The work that computer scientists do, on the work that computer programmers do, and if we consider especially our AP computer science teachers and our AP computer science students, becomes a fundamental way in which they'll write programs and applications, not in Scratch, but in Python, in Ruby, and on Rails, on Swift, and so many other programming languages. So this introduction to computer science captures us because we're able to fly, but really broadens our understanding of computer science and solving problems in the real world as well. Super powerful, super fun way to go about this. But that's fine and good to see on the computer. Really, really fun. What about flying our actual drone? What about when the rubber hits the road and we want to see the drone in the air? Makes sense for us to actually connect our drone and see the drone in action. I have a drone with me right on my desk, so we're going to connect to that drone and share that flight. The cool thing about our drone is that we're able to fly it manually. We're able to continue to keep our drones firmware firmly up to date so that we're generating really good flights time in and time out. That becomes an important part of what we do. And then we're able to record video and photography, expanding the usage of our drones just beyond physical motion and thinking about balance systems, but using this as a scientific tool. We do all that through the Tello application, available on iOS and Android. With our smart devices, this power really comes into our students' hands. What we can consider now then is the ability, and I'm going to change my screen share one more time so that we can see this, to actually program in, to jump into the program, I should say, and see our drone in actual flight. I've got a real drone connected here. You can see my desk. And this is the first person view of our drone in manual flight. I'm flying right in the context of my office, so you're going to see maybe a little bit of a messier desk than what I might like to see. And we'll see some lights. And you might see a very confused dog wondering why there's a flying machine in the office where his dad is working. With a simple swipe, our drone takes off and is in the air. And with really gentle and firm controls, we can get a better sense of what's in the office, including my wife's work area. My office is not big. We're considering a space that's probably 8 feet by, if I had to guess, maybe 11 feet or so, and I can manipulate this drone easy through space just using my thumbs on a smart device. When we're flying drones and we're using technology in the context of our classroom for project-based learning, we want technology that we know is going to last and is going to work really well for our students. That means the equipment that we use, drones that are made and manufactured by DJI, the leaders in drone technology in the United States, but also internationally, means that we're flying drones that solve real problems, that can actually stand up to the day in, day out usage of our students, and that reflect drones that they use in the real world. These DJI drones, this particular drone called the Tello, is something that makes sure that our students are experiencing a drone that's flying with fidelity, or not flying toys, or flying tools. And we're able to record video, record not audio, but also take still photos of our drones as well. So that's just a quick little flight demonstration to show what we would see from the context of our video, right from our drone application as well. This is real technology, real coding experience, real drone flying experience that our students would have the ability to participate in. Now, with those two basic skills, this idea of flying the drone both manually using the Tello application that we just saw, or simulating the flight and then taking that code and pushing it into our drone via the Drone Blocks application. We might have a really simple driving question that evolves. And this is a great place to start if we've never done any kind of drone flight and drone coding in the context of our classrooms before. We might just start with a can question, just the overarching infinitive questioning of the ability. Can we fly the drone to establish a minimally safe environment in which to operate the drone? And this goes right back to what we always talk about with hands-on learning in the context of PBL. One, that it should be student-driven, but that it's hands-on learning and we're going to be learning by doing. We're not going to establish this as a question that means that we have to research a bunch of questions and rely on the words of experts or rely on regulations that may have been written by the FAA, which is really important. When we use a technology like drones, we have to consider how to use this technology safely and responsibly. But as teachers, as educators, as community members, we actually want to get the drones in the air and explore the idea if whether or not we exist in the world, in context and an environment that allows us to operate our drones safely, to operate our drones responsibly, to operate our drones in ways in which our community members agree with and which we can agree with. And what we've shown, just through some simple coding, flying a drone in a short area of simulation, ways in which the drone would fly in real life, and then flying a manual drone in a relatively small amount of space, is yes, we can fly these safely. We can explore even more robust and interesting PBL problems, deeper and interesting questions, even though this question is interesting in and of itself. If you use this question as the driving question for a PBL, we would consider things like ethics and laws and legislation and future applications and the science and the physics involved in all types of different drones, what it would take to actually fly the drone and to establish a minimally safe flight environment, and whether or not that's even the right thing to do. We take all that into account, but at the very basic level, what we understand is that working with an emerging technology like drones, like what we have in our curriculum, or whether it's robots or 3D printing, gives us the ability to get hands-on and really dig in and make this learning real for our students as we go. One thing we also really think is important with respect to project-based learning is the fact that we have to be flexible for situations that might lead to distance or hybrid learning or remote learning scenarios. We never, ever want to be in that situation again, where because we weren't thinking holistically and weren't prepared for futures that we can't predict, that we're kind of left in the lurch when it comes to STEM education. The great thing is that project-based learning, being student-driven and having a diversity of different learning and events, those student-driven activities and learning moments, means that we're able to diversify and leverage the technological tools we've gotten so good at in the past year to really deliver STEM with high confidence and high fidelity, even in a hybrid remote model. When we design lessons, and everything that we do at NextWaveSTEM really falls in line with the 5E lesson pedagogy, where we're engaging our students at the beginning. We're giving them that hook, and project-based learning does a really good job of that in the driving question, attacking different parts of the driving question and actually sharing our thoughts or really presenting new information that's relevant to the technology keeps that fresh for our students. But we explore. We dig into the information that may or may not be news to our student, and we allow them to help teach us as well through the diversity of student work that they've done. In the explain, we're building those cause and effect relationships. Why are things the way they are? Why is legislation written the way it is? Why is the drone the size that it is? And what kind of real world physical limitations, whether that be through the power of batteries in drones or through the power of the free market with price, makes drones look the way that they are. We elaborate and we turn things over to hands-on student work. What kind of flying can you do? What kind of programming can you do? What kind of learning experience can you build that helps reflect that you've synthesized that information and are able to generate new information? And then we assume, as educators, I should say, we as educators have this ongoing opportunity to evaluate our student work. Not necessarily assess, because there's a place for the good assessment that we need, but we're always evaluating and helping our students be steered in the right direction. In the online learning context, that means that we have students that will engage with us via the computer screen and really keep that hook. We'll explore by really presenting that new information and sharing the learnings that we've had from previous lessons, or what we're garnering and what we're ideating. That can be live and through our group chats using tools like Zoom. Small group collaboration becomes huge when we think about breakout rooms, whole group live instructor, learning new skills in drone programming or in research or in presentation, learning how to use new tools to express ourselves and to let our students express ourselves becomes really important when we get into the explain section. The independent work of our students, and especially in the hybrid learning scenarios, this becomes powerful. The ability to prepare an actual hands-on learning activity through simulation, through saving code, knowing that we're going to be hands-on at some point later on in our schedule to actually execute that code, gives us dual evaluation and assessment moments. What does our preparation look like? What does our execution look like? And then our evaluation, leveraging things like our LMS. Older tools like email will also allow us to continue to give our students really differentiated and individualized feedback. We had an example more abstractly about a real world problem students could engage in. But more concretely, it all goes back to this idea of citizen engineering. That could be exploring ways in which drones might be used for essential delivery to disconnect a population, something that we saw pop up a lot in the context of the pandemic in the last year. But once again, going into public policy engagement with respect to emerging technology. What does drone flight mean for privacy? What does it mean when we balance public safety applications versus individual liberty? And what does it mean when we actually have to explore the growth of different aerospace applications, even into space exploration? These real world problems are not limited. We're not locked out of any of these discussions because of the longitudinal nature of project-based learning. We've got time to really, really dig in. We talked about Explorer before, using things like whiteboard tools or even our Google Workspace tools or Microsoft tools will allow us to really collaborate and design our experiences really well. Same goes for our Explain as we're building our work and sharing our code, modifying, changing our presentations, changing our research work, recording our observations from interviews. Our technology helps us with that. And then our LMS allows us to really take in and synthesize that information for our students, all out offering our evaluation as well. All the technical tools for project-based learning are already there. We just need to build the pieces that will work for your students and for your instructors. So lots of information is to really take in there and think about, but at the very least, we've got a great foundation to begin with. How can we help at NextWaveSTEM? How can we move you to a place where emerging technology, especially in the context of project-based learning, becomes a thing that you, your students, and your educators are doing on the regular? Well, the first is that we want you to consider different kinds of technologies that are available through our courses. We have a plethora of courses that really fall into 4 what we think of as themed areas. Courses K through 12 in robotics and artificial intelligence, when we think about the hard terrestrial engineering courses. When we think about working in the sky through combining ideas in computer science and programming, we've got courses that are running K through 12 as well. We make a turn towards 3D technology and design and 3D printing, courses 3 through 12 that are really, really interesting. And new this year, we have courses built out in innovation, where our students explore themes like solar power or exploration of entrepreneurship. What are ways for our students to actually generate new ideas that might not have existed before, to explore new solutions? Our courses are there for you to actually really hook your students' interest as they explore different methodologies and modalities in STEM. All of our courses, as they're scaffolded and aligned to their grade bands, build in this really taxonomically correct progression of knowledge, where our students that are K through 12 are just being introduced. Our 3 through 5 students are discovering, they're learning more about application. Our 6 through 8 students are actually synthesizing and analyzing the use of technologies towards applications. And our 9 through 12 students are actually creating solutions. We're building up and scaffolding based on their prior work, based on their level of development, and based on what our technologies actually allow our students to do. Our courses are turnkey solutions for you to implement in your schools. You can license the course, it can be yours to use. Each course comes with between 10 to 15 lessons for in-class delivery, equipment for your entire class, whether that's drones or robots or any equipment that's associated. But additionally, we're giving you the training that you need. That's training in your technology area, access to our learning management system, and year-round implementation support. We don't drop you off and leave you. We're there to walk through this with you. But we're also running Reteach Delivery options, where NextWaveSTEM courses can be delivered virtually to your students that are in person in your schools. That means that we're bringing in a wealth of expertise in their instructional experience with our NextWaveSTEM courses, but also with their experience as STEM professionals. These courses can be done with or without equipment, but we can customize what you need. The exact equipment that you'll need to deliver the courses, the exact level of engagement, and build a program that works for you, whether that's in school time or out of school time. For those who are joining us for Kentucky, this is a great place to really explore pilot opportunities. And we'd love for you to connect with our school partnerships manager, Jim Sheehan, to learn more about those opportunities. Jim is a great guy. I'm actually going to drop his email address in the chat so that you can email him and potentially learn some more. With that being said, sprayed you with a fire hose of information. We're running quickly towards the end. Got a little bit excited there and was really happy to do a couple of physical demonstrations so that we can see the technology in action. But I do want to quiet myself for a few moments and leave the floor open, both in the chat and via the Q&A for any questions that you have. So I'll pause and we'll let those fingers start flying for any questions. Once again, sorry, we won't be able to hear your voice, but we would love to hear any questions and read any questions that you might have via the chat. Well, I'm not seeing any questions fly through right now, but that's okay. That just lets me know that you all are deep thinkers, that as you're reflecting on this hour that we spent, that you're going to have some questions that come up a little bit later on, and you're going to shoot an email to either Jim or myself. The great thing about both of us is that we are really easy to reach. My email is super simple, desmond@nextwavestem.com. My colleague, Jim Sheehan, is really easy to reach. He's jim@nextwavestem.com. I'm be including both he and my contact information via the follow-up email with this presentation that you all will be receiving. If you get struck with that eureka moment and you have questions, we'd love to answer them. You can get into the weeds with us. We'll dig into those questions and answer them the best that we can, and maybe even do some ideation with you. You can find NextWaveSTEM on all major social media outlets @NextWaveSTEM. That's on Twitter, that's on Instagram, LinkedIn, and Facebook. We're not on TikTok. I neither tick nor do I talk, but that's something that we always say that we might have an intern do. Our previous intern from the summer didn't quite get to that task, but we might get there one day. All that to say is that we would love to connect with you. To all of us, all of you who are able to join us for this hour, considering project-based learning, we're so thankful for your presence. We're so thankful for your attention and your consideration. We're hopeful that you continue to walk down a path where STEM learning becomes real for your students. They're exploring the technologies hands-on and engaging in fun ways, in ways that really move the needle, solving problems both at home and really, really far. Until we get a chance to speak again, we're hoping that each and every one of you stays safe and has fun teaching STEM. Thanks so much, everyone, and we'll talk to you again soon. Bye-bye.